Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is triangular. We will look at Pascal's triangle, one of the oldest mathematical constructions around, having appeared in a 10th century book by the Persian mathematician Al-Kharajhi and Indian manuscripts dating back to 200 BC. The construction of Pascal's triangle is simple and well known. Start with two diagonals of ones, dropping down from a single one. Everywhere there's a pair of numbers, add them together and write down the sum on the line below between the two numbers. So a 2 goes below the 1 and the 1 from row 2. A 3 goes below the 1 and 2 from row 3. The first 11 rows are shown here, but the construction can go on forever. This is good for practicing addition, but what makes this a timeless classic? Mathematics is about patterns, and there are numerous patterns to be found here. A simple one is to start on the second row and follow a diagonal down. 1, 2, 3, 4, 5. Those are the counting numbers. Now let's add the numbers in each row. 1 plus 1 is 2, 1 plus 2 plus 1 is 4, 1, 3, 3, 1 makes 8, and so on. Then we got 16, 32. These are all the powers of 2. We will see shortly that this is not an accident. What if you alternate adding and subtracting? So 1 minus 1 is 0. 1 minus 2 plus 1 is 0. 1 minus 3 plus 3 minus 1 is 0. You're always going to get 0. Again, not an accident. Here's something more complicated. Let's do the triangle mod 2. What that means is to write in a 0 for even numbers and a 1 for odd numbers. Here's what it looks like. Do you see anything? Well, starting in the 5th row, there's an upside down triangle of zeros. In the 9th row, another triangle of zeros is starting to form. Here's a bigger snapshot from Math Stack Exchange, even numbers colored blue. This pattern of nesting triangle is reminiscent of Sierpinski's triangle, a fractal discussed in another episode. Speaking of connections to other episodes, adding two numbers to get the next number should remind you of the Fibonacci sequence. To find the Fibonacci sequence, make the triangle a right triangle and add the numbers on a diagonal as shown. There they are. Why does this work? Now, in this format, the addition defining a triangle is done in a right and down pattern. For example, start at a green 6, go over to the blue 4, and then down to the black 10. 6 plus 4 is 10. We could do the 10 in black plus the 5 right next to it and go down to get the sum 15. Now, let's look at the blue numbers that sum to 21. The blue 6 comes from the green 5 plus the red 1. The blue 10 comes from the green 6 plus the red 4. Every blue number is formed by a green plus a red. The diagonal sums then follow the Fibonacci sequence. We'll look at Pascal's triangle in three ways. Construction, as we did above, binomial coefficients, and combinations. For binomial coefficients, we need to review some algebra. Remember how to FOIL, x plus y times x plus y. You do the first, x plus x, then the outer and the inner, which are x times y and y times x, and then the last, y times y, which we can write as x squared plus xy plus yx, or 2xy plus y squared. If we multiply out three of those, we'll get that x plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. Now look at the coefficients in these. For the square version, we see a 1, 2, 1. And for the cube, we've got 1, 3, 3, 1. Those are rows 3 and 4 of Pascal's triangle. This pattern actually works for any power of x plus y. So a quick way to get x plus y to the 6th is to look at row 7 of Pascal's triangle, 1, 6, 15, 20, 15, 6, 1, and multiply by increasing powers of x and decreasing powers of y. So x plus y to the 6th is x to the 6th, 6x to the 5th times y, plus 15x to the 4th y squared, 20x cubed y cubed, and so on. Returning to one of the patterns we saw above, what happens if you plug in x equals 1 and y equals 1? Well, on the left, it's 1 plus 1, 2 to the 6th. On the right is 1 plus 6 plus 15. That's the sum of the numbers in the 7th row, and we get it equal to a power of 2. So clearly that will always happen. What if x is 1 and y is negative 1? Well, on the left, you're going to get 1 minus 1 is going to be 0. On the right is the alternating addition and subtraction of the coefficients, one of our other patterns. In the non-transitive episode, we talked about a game in which I have a probability of 2/3 of winning each round. My odds of winning overall can be improved by making it a best 4 out of 7 series. One of the ways to win the best of 7 is to win 3 of the first 5 and then win the 6th, making it 4-2. Let's look at the probability of winning in 6 rounds. That means I lose 2 of the first 5 and then win round 6. One possible sequence is win, win, loss, win, loss, win. Plugging in the individual probabilities, the probability of this happening, assuming independence of rounds, is 2/3, 2/3, 1/3, 2/3, 1/3, 2/3. Since the order doesn't matter, we can write this as 2/3 to the 4th times 1/3 squared. Of course, there are other sequences of wins and losses that could occur. For example, win, loss, win, loss, win, win. Filling in the probabilities, 2/3, 1/3, 2/3, 1/3, 2/3, 2/3. Again, we can write that as 2/3 to the 4th times 1/3 squared. So when I'm adding these together, I'm adding the same thing. I just need to know how many there are. We're going to get as a final answer 2/3 to the 4th times 1/3 squared times the number of orders of wins and losses. So we need the number of orders for 3 wins and 2 losses, meaning 3 wins and 5 games. This is called 5 choose 3 and is written in parentheses 5/3. Amazingly, you can find this on row 5 of Pascal's triangle, the row with the 5 in it. It's going to be the 3rd entry if we start counting at 0. So 1, 5, 10, 10, that's our number. Our probability answer is 10 times 2/3 to the 4th times 1/3 squared, which is about 0.22. Now that you know the shortcuts, you can compute the other probabilities very easily. Much of the power and beauty of math comes from finding different ways to look at the same problem or quantity. So having the combinations interpretation of Pascal's triangle lets us easily triangulate the answer to a probability question. We'll finish with another nice pattern in Pascal's triangle, fittingly called the triangular numbers. Start at the top and count the numbers in the triangle from the top down to an end row of your choosing. If you stop at row 1, there are 3 numbers, all of the ones. Go down to row 2, there's now 6 numbers, as highlighted. Go down another row, you have 10 numbers, like the 10 pins in a bowling alley. The numbers 1, 3, 6, 10, 15, and so on are called the triangular numbers. Now, something called triangular should be easy to find in Pascal's triangle, and you can see them by starting in row 2 and following the diagonal. 1, 3, 6, 10, 15, 21, and so on. The hits keep coming.